Okay, so we're just over a minute past the hour, so we can get started for today's ENLA seminar. So I'm Alex Townsend at Cornell University, and I'm chairing today. So our speaker is Daniel Kressner, who is a professor at the Institute of Mathematics at EPFL. Daniel is, of course, very well known to all of us for his work on eigenvalue problems and algorithms that use low-rank tensor formats. In particular, Kressner has helped out me a lot with his 2013 literature survey paper, which is a short survey titled A Literature Survey of Low-Rank Tensor Approximation Techniques. And this is extremely helpful if you want to fast track your literature survey if you're writing a tensor paper. It contains most of the good papers pre-2013. He was also just elected as a Siam Fellow for his contributions in numerical linear algebra and multilinear algebra, as well as scientific computing. So many congratulations for that, Daniel. In addition to all that, of course, Daniel was one of the founding members of the ENLA seminar committee, and he stepped down in December. And the new committee thought, since he stepped down and he's no longer in the committee, he's opened himself up to get an invitation to talk here. And so here we are. We're looking forward to your talk, Daniel, on randomized joint diagonalization. The Zoom window is all yours.
Okay, thank you, Alex, for the very nice introduction. And I thank the committee for giving me the opportunity to talk in the seminar series, which was recently termed the best thing that happened due to COVID, and recently at Sime News, I believe. So I'm going to talk about randomized joint diagonalization, and this is joint work with my collaborator Haoze He at EPFL. And let's get straight into it. So some of you may teach it in the algebra, some of you may not, but there's this very basic theorem that two symmetric matrices AB commute if and only if they can be jointly diagonalized by an orthogonal matrix. And if you think about the proof, one direction is easy, right? If you can diagonalize them, it's clear that diagonal matrices commute. So that's the easy part. And the other part, some of you may have forgotten. So you kind of look at an eigenspace of A, and you show that it's an invariant subspace of B. That's one way to prove it. Or another way is to kind of start block diagonalizing A. So you pick one eigenvalue, you take all the eigenvectors, then you get an invariant subspace belonging to a single eigenvalue. This block diagonalizes A. A22 doesn't contain lambda 1. And then you can show that B needs to be block diagonal simply because AB minus BA implies that A22 minus lambda 1 identity BT1 is equal to 0. And since this matrix is invertible because of this condition, B21 needs to be 0. And so then you can just diagonalize B11, and then you proceed by induction. So that would be one way to prove it. And this would be the procedure. So here we have two matrices AB, they obviously commute. They are not yet diagonal. So you would just diagonalize A and group multiple eigenvalues together. Well, you actually should group these three together here. And then you diagonalize the blocks of B which are not yet diagonal. And hence you get the joint diagonalization of A and B. The problem is if you move from linear algebra 101 to numerical linear algebra, that it's very hard to encounter commuting matrices unless they have like integer entries or so. But in the moment you store it on the computer, you are going to lose exact commutativity. There could be other things. Often commuting matrices arise due to modeling assumptions that signals are modeled to be some stochastic processes, and then there are some commutativity assumptions. We have measurement errors in signals. So a more reasonable assumption is that A and B nearly commute. And if you think about what does it actually mean that two matrices are nearly commute, you arrive at an interesting question. It's not exactly related to my talk, but it's fun. So I thought I include this. There are two notions. They have been given precise terms in the literature. So one way to commuting is say, okay, so the commutator needs to be 0. So you say A, B are almost commuting if the norm of the commutator is small. It would be very reasonable, very easy to measure. It doesn't really fit the model of where you say, okay, maybe you lost commutativity because you just stored A and B on your computer due to roundoff error. Then the second model would be more reasonable to say that A, B are nearly commuting if there exist perturbations delta A, delta B that are small, which make A and B commute. Now this is a good model. I would say this is a better model than the almost commuting, but it's very difficult to test. So you kind of need to optimize over all delta A, delta B, and try to find the minimum delta A, delta B, which enforces commutativity. Now, if you think what is the relation between these two concepts, and this is the fun part, one direction is very easy. Essentially, a triangle inequality. If two matrices are nearly commuting, they are of course also almost commuting with essentially the same level of error. But what about the opposite direction? So if we have a small commutator, does it mean that A, B are nearly commuting? So is it easy to check whether two matrices are actually nearly commuting? And the answer is, well, it depends. So there are a number of results in the literature from operator theory and mathematical physics. There's a negative result if you remove, if you don't impose any symmetry on A and B. There's a construction in this paper by Choi, which where A is diagonal, B is upper bidiagonal, where A and B have norm roughly 1. The commutator is small. It's arbitrarily small as n increases. But you are not able to find perturbations which make this commuting, small perturbations. So all perturbations are must have norm close to 1 actually. So you're not going to find a perturbation of norm 1 divided by n, which makes these two matrices commuting. On the other hand, there are kind of positive, or let's say semi-positive results when you impose further structure on AB. AB are symmetric or Hermitian. First qualitative result from 95 by Lin, and more recently a result by Hastings. I will comment on this a bit in more detail. So you kind of suppose that AB are normalized. The norm of the commutator is delta. And then Hastings has showed in a quite complicated construction that there are symmetric or Hermitian perturbations, delta A, delta B, which make A and B commute. But instead of delta, you get delta to the 1/5. So you kind of maybe, you see the norm of the commutator is 10 to the minus 15, but I actually need a 10 to the minus 3 perturbation to make them really commute. This is a bit fun because Hastings published a paper in 2009 with delta to the 1 to the 6, and 2 years later, there's an unrefereed archive preprint which claims delta 1 to the 5th. So you're invited to try to improve this. Plus, the result does not extend to free matrices. There are counterexamples, even if the matrices are symmetric. So looking at all the possible commutators is not going to tell you a lot about whether these matrices are nearly commuting. Now let's have a look at nearly commuting matrices. So I took the matrices from before after we diagonalized them. Just for the fun of it, I added 10 to the minus 12 and 10 to the minus 8 on the diagonal. So we have some not identical eigenvalues, but a cluster of eigenvalues close to 1. And then I transform these matrices to hide that they are diagonal. I choose a random orthogonal matrix Q. So if I would carry out this transformation in exact arithmetic, A and B would truly commute. So the commutativity is purely destroyed by the roundoff error when you apply Q and you save AB after the transformation on the computer. So they are nearly commuting up to a level of 10 to the minus 16. Sorry. And now you could take these matrices and run the linear algebra 101 procedure on that two matrices. So we would start by diagonalizing A. So I neglect everything around 10 to the minus 15. So you get some 4 of 10 to the minus 15. If you compute a matrix V and you apply it to A, I neglect all this. So you kind of recover the diagonal structure of A pretty well. But when applying it to B, you're actually not getting something. So what you would like to see is some block diagonal structure. And B only has diagonal blocks where A has identical eigenvalues. And it's not holding anymore. So what you see is that you have a block here, which has 10 to the minus 8 off diagonal entries. But in this corresponding block of A, the eigenvalues are not identical up to roundoff L. So these are symmetric matrices, so the eigenvalues are not ill-conditioned. This is not a problem here. So you can decide to perturb A to make them identical, and then you diagonalize B, or you can decide to neglect the off-diagonal entries of B, and but that's going to introduce also an error of 10 to the minus 8. So even though you know that the matrices A and B are nearly commuting up to a level of 10 to the minus 15, this linear algebra 101 procedure is not recovering it. You can start with A, you can start with B. In both cases, you will realize that you're stuck with an error of 10 to the minus 8 in this procedure. And it's not easy to fix. You can kind of start clustering and try to massage things a bit, but it's not going to fix the problem. And the idea of this talk in a nutshell is to, instead of looking at starting with A or B, you start with a random linear combination of A, B. So I'm going to choose mu1 and mu2 to be just a standard normal distribution, independent. I combine A and B, compute V, which diagonalizes the symmetric matrix. And then I apply V, matrix V, which I get, I apply to A, V transpose AV, becomes diagonal up to a level of 10 to the minus 15, which is neglected here. And the same for V transpose PV. So suddenly, instead of starting with A or B, I start with a random linear combination. I get perfect recovery up to the level of roundoff M. That's kind of the idea of this talk, is to explore this a bit further on the algorithmic and on the analytical side, this phenomenon. It's not special for, it's not only holds for the special matrices, but it's a more general observation. So to set up things a bit more formally, so we are not looking only at two matrices, we look at a family of nearly commuting matrices where D in total, A1 to AD, they are all n by n. And I want to find an orthogonal matrix V that nearly diagonalizes A1 to AD in the sense that the off-diagonal parts of the transformed matrices A1 to AD are small. This has a number of applications. Probably the most famous one is blind source separation, where different techniques which all lead to the need for joint diagonalization can be used to separate, to unmix signals. Something which became quite famous to use these techniques to compute orthogonal decompositions of moment tensors. I think Tamara Calder wrote about this, but there's even, I think, a whole book by Anand Kumar about these techniques. And you find it in other parameter identification, manifold learning. There's even a paper on computer graphics where these techniques are used. And most existing, not all, but I would say almost all existing algorithms for this problem are based on optimization. It's saying, okay, well, maybe this is not such a great, nice, neat linear algebra problem. Let's just take a step back and formulate an optimization problem which aims at addressing this problem. So you would kind of optimize over all orthogonal matrices, so kind of on the manifold of n times n orthogonal matrices. And then you have some loss function which measures how far are you away from being diagonal. And the most natural criterion is that you would just look at the off-diagonal parts. So you just set the diagonal parts to 0. Essentially, this off-diag sets all diagonal parts, diagonal entries to 0, and measure the Frobenius norm of the off-diagonal part, and then you combine the Frobenius norm for all the matrices. In the case that A1 to AD are symmetric positive definite, you can think of them as covariance matrices of multivariate Gaussian distributions, and then you can use things which compare distributions like the KL divergence. And this was observed by Pam 2001. This was a seminal paper in the area to actually consider this metric here. which looks at the diagonal part, the determinant of the transformed matrix, and the determinant or the product of the entries of the diagonal entries. And if you look at this a bit longer, you will see for symmetric positive definite matrix, this becomes zero if and only if the matrix V transpose AKV is diagonal. And this criterion is when you want to learn something about multivariate Gaussian distributions, arguably this criterion is better suited. Now you have a target function, or you can run an optimization method. And for those of you who work for a couple of years in the linear algebra community, probably the first thing that comes to your mind is a quite famous paper by Bunse, Gerstner, Byers, and Mehrmann from the 90s, which takes the perspective of Jacobi algorithms for diagonalizing a single symmetric matrix and trying to extend this, and can be viewed as applying coordinate descent techniques to this optimization problem by writing V as a product of Givens rotations. Then you would alternatingly optimize the Givens rotations to bring L as small as possible. PAM, together with the objective functions I've shown to you for symmetric positive definite matrices, also developed the block coordinate descent techniques. Now, as we will see, especially the first Jacobian methods are actually not working extremely well. And more recently, there have been many papers on looking at this problem. Some have developed Kressner-Newton methods for both target functions. And since V lives on a manifold, you think immediately about Riemannian optimization, and then all sorts of Riemannian optimization techniques, first order, second order, Kressner-Newton methods have been developed for that purpose. Later on, I will show you a comparison, a numerical comparison to some of these methods. And there are many more. There's been really an explosion. If you're not mentioned and you worked on this, I apologize. There's been really an explosion of research during the last 10 years on this topic. Now, we are not using an optimization approach. We are using a much simpler approach. One problem with the optimization approach, if you use second order methods, it's very expensive to optimize O of n square variables. And the other disadvantage is that you have to program quite carefully so that it performs well. You have problems with global convergence, etc. So here we are trying a much simpler approach. We just take these D matrices. We make a random linear combination. Now here more generally, so we take mu. This is a vector with IID variables from the standard normal distribution. And we look at this linear combination, and then we diagonalize the symmetric matrix. So this is like 2 lines in MATLAB, or you can even fit it in 1 line. I think convenient without looking very awkward. And it turns out that V, this matrix V, is often a good approximate joint diagonalizer. So it doesn't only diagonalize A of mu, but it actually diagonalizes each of the individual matrices if they are nearly commuting. And this idea is not new. This has been often used in ad hoc fashion to initialize optimization methods. More explicitly, it has been used in the context of parameter identification problems. It has been used in the orthogonal decomposition of tensors by Anand Kumar, for example, in her work. But related ideas also appear in situations where maybe you don't use an orthogonal transformation, but a more general similarity transformation. Then you can compute other stuff like CP and related decompositions for tensors. In this context, randomized linear combinations have been used as well. So even for multivariate root finding, there's the so-called joint eigenvector method, where you build a couple of matrices, and then you know that if there's a root, these matrices have a joint eigenvector and is closely related to joint diagonalization. And this random linear combinations idea have also been used in this context by quite a few persons in this area. And there are many more examples where this approach has been used as an ad hoc idea, either as an algorithm itself or maybe for initializing an optimization method. And why does randomness help? And qualitatively, you can see this quite easily if you look at a family of 2x2 matrices. So I have the 2x2 matrices that commute exactly. And then we have 2 situations. So one situation that every matrix has double eigenvalues, but also the eigenvalues are symmetric. So necessarily the matrices are diagonal. They're actually scaled identity matrix. You can just use a random orthogonal, any matrix V you come up with will do. It will just not destroy the diagonal structure of A1 to AD. So this is really a fantastic situation that you have exactly double eigenvalues. Now, the other situation is that at least one of the D matrices has two simple eigenvalues, two distinct eigenvalues, and then you take a random linear combination, and you must be very unlucky that maybe you don't take this matrix into account, then mu k needs to be 0. This happens with probability 1. If you take a Gaussian random variable mu, it's not going to be 0 with probability 1. Or you have cancellation. But cancellation, because there's some other matrix which also has two distinct eigenvalues, are just are very unlucky that you take a linear combination and they're going to have double eigenvalues. That also happens with probability 0. And so for the exact commutativity, this procedure actually works with probability 1. You'll find a more formal proof in the work by Anand Kumar. And our contribution is an analysis when A1, A2, and AD only nearly commute, that where we can say something. There has been some prior analysis if you assume sufficiently large eigenvalue gaps. So for example, if you say, okay, all matrices have distinct eigenvalues and where the gaps between the eigenvalues for each of the matrices A1 to AD is sufficiently large, or some linear combination is going to give you a matrix with sufficiently large eigenvalue gaps. So there has been work and analysis on this, but you also see that from this exact commutativity case that it doesn't look like that eigenvalue gaps are really necessary, because if you have double eigenvalues, that's actually a great situation for joint diagonalization. So there are some indications, or maybe this may not be necessary, and this is what we worked on. I would like to give you some idea why in the nearly commuting case, actually these gaps do not play such an important role, even though we are going to use it in the analysis in the beginning, but then they cancel out. So let me just set up a bit the mathematical setting. So we have matrices AK, they are nearly commuting, which means that there are commuting matrices DK, plus some small perturbation. We measure the perturbation by just taking the squared L2 norm of the Frobenius norms of the perturbing matrices. Now I look at the matrices AK, which are not commuting. I compute an eigenvector I assume for the moment that it's associated with a simple eigenvalue, at least as epsilon goes to 0, and look at a linear combination. So, and I look at the corresponding linear combination of dk and ek as well. So I decompose A mu as D mu plus E mu. And what I want to show is that this x tilde, which I computed from A of mu, is also a good approximate eigenvector for each of these individual matrices A1 to AK, AD, because that means if you use this as a transformation, then the corresponding off-diagonal parts in the transformed matrices are going to be very small. If you, for example, look at the residual, the norm of the residual will pop up in the corresponding off-diagonal parts of the orthogonal transformation, where you choose maybe the first column to be this eigenvector x tilde. Now we want to look a bit at this x tilde a bit further. So it's going to be approximately an eigenvector of d of mu up to some perturbation, which is introduced by E of mu. And then you can just look at the seminal book the famous book by Stewart and Son from the 1990s, which contains a lot about eigenvector perturbation analysis. And you will find a formula which tells you that there's an exact eigenvector of d of mu. Remember, this was the linear combination created from the commuting matrices, somehow the good guy, the unperturbed guy, for an eigenvalue of that combined matrix, which differs from x tilde by this term. And there's some dangerous term here, which looks dangerous. It's a term, we have the pseudo-inverse. So lambda of mu is an eigenvalue of d of mu. So lambda mu identity minus d of mu is going to be singular. And if you think of d of mu a diagonal matrix, it's going to have, at one point, it's going to be 0. That's where lambda mu has been picked up. and at all the other entries you have going to reciprocals of eigenvalue gaps. That looks a bit dangerous, but we are actually not interested in the quality of this eigenvector itself. We are interested that it's going to affect small residuals for each of the individual matrices AK. So I'm going to look, now I take the corresponding component of lambda of mu as an eigenvalue approximation of AK. And I want to show that X tilde is a good eigenvector approximation. So I look at this residual. This requires me essentially to multiply lambda k identity minus dk with this term. And if I diagonalize this matrix, I'm going to get a diagonal matrix. But now this potentially difficult gap terms are counted with the corresponding gaps for this individual matrix dk. So if you look at these diagonal entries, you kind of have the gap for an individual matrix divided by the gap for the linear combination. You push this gap down here, and you're going to get this expression for the diagonal entries. So if you ignore this part here, the lambda k minus ck, this potentially dangerous small gap, is going to cancel out if mu k is not close to 0. So if you ignore this part, this fraction is going to stay modest. You don't want this guy to become large, because then this bound is going to get large. In turn, you don't want to get mu k to be small. Mu k is a Gaussian random variable, so you have to say something about the Gaussian random variables not becoming small. So an anti-concentration result about Gaussian random variables. To be more precise, you can rewrite this expression as an inner product between something which contains the gaps and your random vector, but now it's normalized. So it's not going to be a Gaussian random vector anymore, but it's going to be uniformly distributed on the n-1 sphere. To look at this individual entry. And for this, we know a lot of things. So this is the key quantity. This key quantity, we don't want it to be small because it's appearing in the denominator. So we want to show that this doesn't happen to be small if you choose a random vector mu. It happens to be an inner product between a random vector uniformly distributed on the sphere and some fixed vector. And for this fixed vector, what we know is, because if you look at the k element of this entry, this vector has L2 norm at least 1. And then you can look at the distribution of this vector, and bound integral someone else, Dixon from 1983, and in the context of estimating 2 norms of matrices, has already worked this out. And it tells us that the probability of alpha mu, this key quantity here of getting small, which is the bad case, is actually going to be small. So let's be a bit more precise, because if you work in this area and you look at concentration results, you may be a bit spoiled by exponentially decaying failure probabilities. This is not going to happen here. So if you want to have a failure probability of 10 to the minus 3, you only are going to get this by saying, okay, alpha mu is not going to be smaller than 10 to the minus 3 up to a failure probability of 10 to the minus 3. So the failure probability is proportional to what you pay in terms of the smallness of this term. And this analysis can be extended. We just looked at simple eigenvalues. Simple eigenvector can be extended to multiple eigenvalues, where you're replacing perturbation bounds for eigenvectors by perturbation bounds for invariant subspaces. And then you need to do it for all eigenvectors, or all kind of invariant subspaces, collecting the multiple eigenvalues to get the whole joint diagonalization. But then you just apply this result individually and use the union bound. And what we get at the end as a theorem is for precisely the setting which I described. So we have commuting symmetric matrices. AK is a perturbation of that tuple. We take a random linear combination. And then for any prescribed, like you in this randomized results, you always need to allow you some leverage. So that's the capital R here, gives you some leverage to control your failure probability. So epsilon square would be perfect. Should be the same epsilon here. That's not a different one. Epsilon square would be perfect. It would be kind of perfect recovery. We would perfectly recover EK. That's not something you can hope for, at least not with probabilistic methods. So you pay some overestimation factor. So you say, okay, if roundoff error perturbed my commutativity, and I have an error of 10 to the minus 15 here. Maybe I'm still happy with 10 to the minus 14. Then you would choose capital R equal to 10. Or maybe you say 10 to the minus 12 is still good enough. Then you can choose capital R equal to 1000, for example. And then this result tells you that you have a failure probability. So this is going to hold. The good case is going to hold up to some failure probability, which is proportional to R to the minus 1. So if you chose 1000, it's going to be proportional to 10 to the minus 3. There's some ugly term here. There's some dependence on n. We're still working on that to reduce this a bit further. We can probably not, it comes, for example, from the union bound. We can probably not completely remove it, but maybe we can lower it a bit. And so we suspect that this quadratic dependence on n, which is a bit annoying because you have to increase R correspondingly to get some decent success probability here. This is actually not necessary. And you may not like, so if you choose R equal to 10, and you just get a success probability of 0.9, you may say, well, 0.9 is not really what I would consider what I would consider as a robust method. But it's easy to decrease the failure probability rapidly by just repeating the experiment, right? In terms of using one random linear combination, you choose capital L random linear combination, and the failure probability reduces from R to the minus 1 to R to the minus L, times some factor, of course, times some constant, of course. And that would be kind of the basic algorithm. So in practice, we are not going to choose capital L very large. What we see is choosing capital L equal to 3 often does the job. So this whole joint diagonalization, instead of using some optimization method, you just can choose 3 random linear combination. You pick the best one. The best one you can look at which minimizes the off-diagonal part, or equivalently, which maximizes the diagonal part, and which reduces a bit the cost in this testing here. And I return the best candidate among the L. And so you can only fail if all L events fail, and that's why the failure probability reduces drastically here. Unfortunately, the dependence on R cannot be improved. So this is actually tight, this dependence on R. So here we plot the empirical failure probability. So we look whether this bound is satisfied with a right-hand side multiplied with this capital R. So we prescribe some perturbation, let's say 10 to the minus 10, and we declare success if for I equals 100, if the off-diagonal part does not exceed 100 times 10 to the minus 10. And then we run this 1000 times, and we count the number of failures, and that would be the empirical failure probability. And for one linear combination, that would be the curve corresponding to R to the minus 1. And this is the empirical failure probability, which really follows this curve. So you're really not getting anything better. The bounds are tight, asymptotically tight in this sense, up to some constants, of course. And if you increase the number of tries, okay, so that would this was R to the minus 1, and if you increase, you get R to the minus 3, and then for 100 you get a failure probability of 10 to the minus 5, which is pretty good. Let me emphasize something about the main result, which I forgot, is that because of this dropping out of the gaps, you're not seeing a gap here, right? So this first order term is independent of any gaps, any properties of AK, except maybe for n, but there are no gaps here, unlike previous results. Unfortunately, so this is only the first order term. Unfortunately, so far we have not managed to prove that these constants relevant for the higher order terms are independent of the gaps. So what we observe is that this method works very well independent of any gaps, but it could still creep in via the higher order terms in this plot. So this needs to be looked at carefully. And then we refine the algorithm a bit. So it's a bit of a waste if you take 3 random linear combinations and then you just take the winner of this 3 random linear combinations. So why don't you extract the eigenvectors which are sufficiently good from a random linear combination. That's easy to check. You just look at a candidate eigenvector and you look at the residuals for each of the individual AK, and this you declare as a good eigenvector, and then you can deflate the problem and you choose another random linear combination for the deflated problem. So maybe in the first run you only can deflate half of the eigenvectors, and then you need to have another linear combination to deflate the other half. So that would be a way of intelligently combining different linear combinations. There are certainly other ways, but we found this quite effective. So this is an improvement over this very simple algorithm, which works better, but also has a disadvantage that's not one line of MATLAB code anymore. It's maybe 10, 15 lines. And let's let me show you a bit the some experiments to give you an idea how this method works. So for synthetic data, so here we just generated 10 commuting randomly generated 100 times 100 symmetric positive definite matrices. So we choose some randomly chosen diagonal elements which are positive, transform it with a random orthogonal matrix, and in the first experiment it's only perturbed by roundoff error. And what we list here is the timings of the different methods in milliseconds. So these are not large problems. These are just 100 by 100 matrices, just 10 of them. And what you see, for example, here, the Jacobi method, maybe the kind of would be the favorite method of, it comes from the linear algebra community, so would be, so you would hope it's a good method, but actually, so here it doesn't really work very well. So it has convergence problems, it has problems to converge to the global optimum, obviously. So it only recovers 10 to the minus 7. Since the matrices have roughly norm 10 to the 4, the eigenvalues have been chosen, so you would expect something around 10 to the minus 12. So there's 5 orders of magnitude off. It's also very slow. It takes 2 seconds for quite small matrices. Then a similar Newton-like methods for the standard cost function, they are too expensive for this kind of approximation of the, at least for this approximation of the Hessian used in this method. Uses 3 seconds, gets at a good error. One very competitive method we found, as you will see later, is when you use this Palm's cost function, which was based on the KL divergence and only works for the symmetric positive definite case. There is a quite efficient quasi-Newton method by Upton et al. From 2018, which performs quite well, gets a larger off-diagonal error in this case, and also slower than our methods. But you will see this picture will change a bit. So for this setting, our method is obviously the best. It's a factor 20 times faster than the best competitor. So we tried also a lot of other methods and have only selected the ones which are competitive, and it even attains a smaller error. So here we look really, really good. If you increase the perturbation, so here it was only perturbed by roundoff error. Now we increase the perturbation level to 10 to the minus 5 times the norm of the matrices. So you hope to recover something around 10 to the minus 5. This quasi-Newton method based on KL divergence recovers this quite well. Needs 290 seconds. And for our basic method, where we just do a few symmetric eigenvalue decompositions, we are still much faster, more than a factor 10. Attain a slightly worse error, and with this deflation-based approach, this is more slowly because you have to test the residuals all the time. We get an off-diagonal error closer to the best competitor. And again, this Jacobi method and these Newton-like method for the standard cost functions are really not competitive. Similar picture for 10 to the minus 1, except that now, and our bounds do not predict anything else. We have higher order asymptotic terms. Now just running 3 times eigenMATLAB is not going to cut it anymore. Here the error is quite large compared to the best competitor, but its deflation-based approach still does the job at a time which is still smaller than the best competitor. And it's still relatively simple to implement. Here's one. We tested this for a few applications, and the picture is quite similar to this example. So we are often a bit faster, not too much faster, but this deflation-based approach always gets kind of in the ballpark of the best method in terms of accuracy or performance according to the index used in this application. And here's one application which has generated a lot of kind of tasks for joint diagonalization. So this is called blind source separation, where you try to extract original signals from observed mixing of the signals. So you kind of have an unknown mixing matrix and you try to unmix it by finding another matrix P such that B of A is sometimes close to a scaled permutation matrix. This index is one of the way of measuring the quality of B, and a smaller index is better. So you kind of see that you kind of look at this is going to be close to 1 if you only have one non-zero entry in that row or column, and you subtract -2. So this is going to be 0 if and only if you have only one entry in the corresponding row and column. That's one way of measuring the quality of the obtained unmixing matrix B. There are many different methods of estimating such an unmixing matrix. One method has been proposed in 1999 is to look at an estimator for the cumulative tensor for the signals. This is a 4th order tensor, and then you look at slices, and then under certain modeling assumptions, you maybe have to do some whitening of the signals before. Under certain assumptions, you can show that the slices are actually commute under if these modeling assumptions hold. And then you can diagonalize these commuting matrices in order to obtain the unmixing matrix B. And the hope is once the modeling assumptions are not satisfied anymore, you are still going to get a good estimate. So we generated some signals here. The signals have length 5,000 or 6,000, but at the end, this cumulative tensor only depends, the size only depends on the number of signals you have originally and the number of signals you observe. In this case, this is equal to 9. So this is just a 9 by 9 by 9 by 9 tensor. Still, optimization-based methods still need like 0.3 seconds to obtain this. Here, this quasi-Newton method is not applicable anymore because the slices of this tensor are not lose positive definiteness for real data. And what you see here is that this is a really good case that the random joint diagonalization, both variants of our method, are much, much faster by a factor of 20 to 30 and even deliver a better performance in terms of this index. Okay, so this concludes my talk. So let me emphasize that this use of random linear combinations has been around before. But it's not the first time we are considering this. I would say that the analysis and maybe also the promotion of this idea or looking into this idea from a bit more deeply, that's our new contribution. And promoting this idea as a simple and still competitive method to jointly diagonalize symmetric matrices. The asymptotic bound indicates robust joint diagonalization for nearly commuting matrices. At least the first order term doesn't feature any eigenvalue gap. There are a number of open questions. First of all, a fun question is this Hastings exponent for the relation between almost and nearly commuting 1/5. Is that optimal? Good luck with that if you want to look into this. And what would be more important from the perspective of this talk is to have real result non-asymptotic robust recovery, so that if you have an epsilon perturbation, you are able to recover this with an epsilon times constant error in the off-diagonal part without this higher order term. So we haven't been able to achieve this. And now you can think about extensions. So there is work, especially in the context of tensors, to do joint Schur decompositions, to do joint diagonalizations, joint congruence transformations. And at the moment, it's not clear. I think these very beautiful perturbation analysis where the gaps cancel out is not going to hold for this. But maybe something else is holding where one can still show something, or one can carry over some of the ideas presented in this talk. But it's not going to be triviality. Okay, here's some reference, which is hopefully online soon. Thank you for your attention.
Okay, great. Thank you very much, Daniel. Okay, so we can now open it up to the Zoom. Cool. So yeah, thank you very much. Any questions? You can just unmute yourself.
Sorry, what was the matrix B in the signal? Yes, M equal BA. What is B?
B is so B is the unmixing matrix. So actually, it would be the inverse of A or some permuted inverse of A. And so this is the matrix. I have not explained how to. So this is a procedure after the joint diagonalization. You can estimate this unmixing matrix B.
Mm-hmm.
That's the goal of the procedure.
Mm-hmm. Thank you.
Could you, if you don't have positive definiteness, can you add a shift to make him positive definite and then apply the algorithm that needs it?
I think you can do that. I think the problem is that the yes, if you so the problem is that this KL divergence is not going to be a metric anymore for the original data. So I think in a practical fashion you could do that. We have not tried that with this play around with this quasi-Newton method a bit more with shifting. I think from a practical point of view, you could do it. From a theoretical point of view, there may be some problems with interpreting the kind of metric you obtain after shifting.
Thank you.
So you showed that you can improve the probability of success if you do multiple runs. Is there a way of improving the accuracy if you do multiple mus? Because you didn't improve the accuracy there, if I'm right. You just improved the probability of success. So you don't get to improve this r squared epsilon term if I do it multiple times. Is there a way of averaging somehow the multiple runs that you might do with the different mus?
Okay, this is okay. So there are several answers to your question. So the first one is okay. There's going what you want to have is a non-zero success probability, right? So this term here should not get larger than 1. So you have some bound on R, some minimal value of R for this bound. But beyond that minimal bound, you can of course always shift R around. In the you can shift this R into the failure probability, and then you correct for it by doing multiple runs. So once you're above this bound, you can do that. On the second part of the question is very interesting. We have thought about this. So to use some large limit theorem or so in order so you kind of would take multiple runs, and then you would average over the transformation matrices V. So we tried that. So we can try a very simple geometric mean or so of these matrices. It doesn't work. I think there's a problem that this V is actually the V itself is very ill-defined. So you, as you have seen, if you don't have really gaps, so if all the matrices don't have gaps, you get some random linear combination or very small gaps. So the V itself is going to be very ill-defined. So you run several random linear combinations, you're going to get very different V. And you cannot simply average over this V because they are just, it doesn't make any sense. They're completely different. They are just all affecting a very good joint diagonalization. So I think that's a very interesting question. I don't know an answer. It's possible. Would be very nice. Yes, indeed.
Okay. We have plenty of time for more questions.
Yes, and thank you for the talk, by the way. And at the start of the talk, you were talking about the difference between almost commuting and nearly commuting, if I recall. Yes, more or less this. And it fails for generic matrices, yes. But do you know if it's true for determining if a matrix is near normal or not, because normality means just it commutes with its emission.
Oh, okay. This is a bit embarrassing. I should know that. So this is a problem which has been studied a lot in the literature. So distance to normality. What are good measures for distance to normality? Since I would suspect it's not true. It's not so if you have AA star minus A star A is small, that this implies that A is close to being normal. With the same type of proportional to the norm of the commutator of AA star, but let me not comment on this further. I should know it, but now it doesn't come in my mind.
Okay, never mind.
It's a very valid point.
Yes, and another question. Somewhere you said that you wanted the coefficient that you take normal. As in a normal distribution, you wanted that coefficient to be far from zero because they were in a denominator, I think. Yes, here. And maybe taking them with another distribution or something with mean that is not zero may help.
Okay, well, okay, thank you. That was a bit an oversimplified presentation. So the other thing you don't want is that you get cancellation here in this term. And so what you really look at is an inner product between your random vector and some fixed vector. And the only thing you know about the fixed vector is that it has L2 norm at least one, or even so there's an entry which is one. Which is the entry k here. So you have a vector which has one entry 1, and the other entries are potentially smaller. And you take the inner product with a random vector. What you want is that this inner product is not small with high probability.
Yes.
So just I think that increasing the variance may not help too much, or shifting the mean. I don't think it helps too much if you look at the inner products. But I think that other distributions can certainly be used, and there are results on other distributions as well. If you maybe Rademacher will work.
Okay, thank you.
I have a comment to Alex's question about using more random combinations to improve the accuracy. We've been looking with my postdoc Eric Evers into the non-orthogonal variant of this problem, as Daniel mentioned. And there we followed the strategy that we use a random combination and we look for gaps in that setting. And we do a partial splitting at the places where you see
randomized joint diagonalization.
Where you see clear gaps.
Kressner randomized joint diagonalization.
At the places where you see clear gaps, then you use another random combination and you split again. And so if you split enough, after a while, everything has been split and separated that needed to be separated with clear, also with clear bounds on it. As Daniel said, if you don't have these gaps, and sometimes you don't have them, the situation is indeed less clear, but there are still things possible, but this is a work in progress.
Yeah, I agree. I guess for the non-symmetric case, you probably have to look at the gaps. So I would be my
not
guess.
not even. Things are possible. It's not completely lost.
Okay.
So as just a recovery problem, what is the known things about R? So you have an algorithm that shows that you can do it with R scaling like dn squared, and you said that you wanted to have R as a constant. Is there some kind of information theoretic bound that says you can only recover up to a certain constant rather than just silly constant of r equals 1. Is there some way of actually having AKs which you cannot recover precisely? So, or can you do better than D?
I think it's a very good question. So it would be so you would need to prove the opposite result, that the probability that you are bounded by epsilon square. So if I equal 1, for example, that this is going to be very small. We haven't looked at it. I'm not aware that such a result exists. But it's a good point.
I was kind of just wondering if dn squared is the right scaling for r even.
Yeah, I suspect not.
Okay. Very good. Do we have any more questions? We have plenty of time. So, if not, we will. We can stop for today. Thank you very much again, Daniel, for a great talk. Talking about this is the final talk in the spring session for this year. However, we plan to continue in the fall. Obviously, a schedule is yet to be decided, but we'll probably start again around end of August or start of September. So anyway, thank you very much for everyone joining and for making the spring season enjoyable one. Thank you to Daniel and all the other speakers, and we hope to see everyone again in the fall.
Bye-bye.
Bye-bye.